Let's continue now. In the last video, I introduced the notion of Noetherian rings. So let me start by giving a quick recap of the definition. So a ring is a ring R, always commutative ring with 1, is Noetherian if every ideal of R is finitely generated. And the important examples are Z, Q, R, C, any field. Of course, any field is Noetherian. Any field polynomial ring over in one variable or any field. K is any field. Polynomial ring over Z. This last example requires a little bit work, but that also is a Noetherian ring. And a non-example is a polynomial ring in infinitely many variables. So in this video, I want to give some more properties of Noetherian rings. So first of all, I want to start with an equivalent characterization. So another way to check if a ring is Noetherian. So let's define the following notion. Let R be a ring. An ascending chain of ideals in R ascending chain of ideals in R is a collection of ideals like this: I1 contained in I2, contained in I3, and so on. So it keeps on going like this. So it's ascending because I1 is contained in I2, I2 is contained in I3. So I2 is bigger, I3 is bigger, I4 is even bigger, and I5 is bigger than I4, and so on. So it's an ascending chain. It's a chain because each is contained in the next one. So that's simply an ascending chain of ideals. We say that, so the definition continues, we say that the above chain stabilizes. We say it stabilizes if if there exists some integer n such that after n every ideal is same, such that in is equal to in plus 1 is equal to in plus 2 and the rest. So it is basically all ideals after the nth stage are equal. So more precisely I should say that im is equal to im plus 1 for all m which are bigger than n. So beyond nth stage all ideals are equal. So though it's an infinite looking chain, it's only a finite chain. So that's when we say it stabilizes. So the proposition that I want to prove, and this is useful because it will allow us to check Noetherianness in some cases, is that a ring is Noetherian if and only if every ascending chain of ideals in R stabilizes. Okay, so a ring is Noetherian if and only if every ascending chain of ideals stabilizes. So let's check this quickly. The proof is fairly straightforward. So let's do this direction. Suppose R is Noetherian. Okay, so let's assume that R is Noetherian. And let's take an ascending chain of ideals. Let I1, I2, I3 be an ascending chain. So let me write like this: ideals in R. Let this be an ascending chain of ideals in R. And our goal is to show that it stabilizes, right? That's the implication in this direction. I'm assuming R is Noetherian and I want to show that this ascending chain of ideals stabilizes. So let's start with this. Okay, so now what I will do is define I to be the union of In. Okay, so what I'm doing is I'm taking the union of all of these. Just a set theoretic union to begin with. So claim is that this is an ideal. So in general, the union of ideals is not an ideal, because in the ring of integers, the ideal generated by 2 union the ideal generated by 3 is not an ideal, because 2 and 3 are in there in the union, but 2 plus 3, 5 is not in the union, because 5 is not in 2 and 5 is not in 3. But if you take a chain of ideals, their union is an ideal. So let me quickly prove this. What do we have to show? For example, we have to show that 0 is there, but that's okay because 0 is in In, of course, for every n. So 0 is there. Let's say A, B are in I. The main things to check are if 2 elements are in the ideal, their sum is in the ideal. So sum is in the set. So let A comma B be 2 elements in I. That means A belongs to In and B belongs to Im for some n and m. Right? I is defined to be the union. You take 2 elements. So that means if something is in the union, that means it's in some of the Ins. So maybe A is in In and B is in Im. But we know that, so assume, I should write, so assume without loss of generality, n is less than equal to m. Of course, m could be less than equal to n, in which case the argument goes in a similar way. So In then is contained in Im, right? Because I1 is contained in I2 is contained in I3. So if n is less than m, In is contained in Im. So A belonging to In is actually in Im, and B also is contained in Im, of course, by definition. So A plus B is in Im, but Im is contained in I, because Im is one of the factors whose union is I. So A plus B is in I. This is where the chain is important. One element is in In, one element is in Im. Unless you are able to compare In and Im, you can't conclude this. So A plus B is in Im. Similarly, so I will leave this for you. You can quickly check this. If needed, stop the video and check this. If I is in I, A is in I, R is in R, this implies RA is in I. In fact, this is trivial. This doesn't require a chain property. So this proves that I is an ideal. So this we have proved. But I is an ideal in a Noetherian ring. Right? R is Noetherian. That is our assumption. So I is finitely generated. Right? By definition, remember what is the definition of a Noetherian ring? Every ideal is finitely generated. So say I is equal to A1, A2, An. Let me call it AR, where A1 through AR, of course, are elements in the ideal. So let's say A1 through AR generate I. But now A1 belongs to some I. A1 belongs to I means A1 is in I, let's say N1 for some N1. Because I is the union of these I1, I2, I3 and so on. So every element of I is in one of these. Let's say AN1. Similarly, A2 is in IN2 and so on. So in general, AI is in INI. But now I'm going to take N to be the max of N1, N2, NR. So A1 is in IN1, A2 is, N1 could be 100, A1 could be in I100, A2 could be in I23, A3 could be in I42, A4 could be I205 and so on. So I'm taking the maximum of all the indices. That means A1, A2, AN. Remember, this means that INI is contained in IN for all I from 1 to R. Because N is bigger than N1. N is at least as big as N1. So IN1 is contained in IN. Similarly, N2 is at least, N2 is less than or equal to N. So IN2 is contained in IN. So each of them is contained in IN. That means A1, A2, AN are all in IN because they are all in INI, which is further contained in IN. This means the ideal generated by A1 through AN is contained in IN, right? Because if an ideal contains a bunch of elements, every linear combination of those elements is by definition in that ideal. So the ideal generated by A1 through AN is contained in IN. But this is equal to I by hypothesis. I is equal to A1 through AR. I should really write R here. So this is equal to this, but IN is also contained in I, right? Because IN is one of the factors whose union is I. So I is contained in IN is contained in I. That means I is equal to IN. In fact, I should not define N like this. If N is at least this number, max of this, then this argument holds. So that means if you look at this chain, I2 and this number, let's say, is M. So M is that number, you have IM, then IM plus 1, and this is the original chain, but this we have just proved is I, this we have proved is I, IM plus 2 is I, at every stage we have I. This is exactly the meaning of a chain stabilizing. So what we have done is, you have taken a chain, we took their union, which is an ideal, we argued. Once it's an ideal, we have shown that we do not need to show, it's an assumption. Remember, R is Noetherian. Once it's an ideal, it is generated by finitely many elements. The key word here is finitely many elements. Because there are finitely many elements and each of them belongs to one of the ideals IN, we can eventually reach a point where all the generators are in one particular IN. And then after that, we get nothing new, we get just the ideal I. So the given chain stabilizes. So this completes the proof of one direction, right? We wanted to prove that if a ring is Noetherian, every ascending chain of ideals in R is going to stabilize. So now let's prove the other direction. We assume that every ascending chain of ideals stabilizes, and we want to show that every ideal is finitely generated. Okay, this is easier. So let's take an ideal and let us choose an element of I. So let x1 be any element of I. Of course, there are elements of I. I is a non-empty set, right? An ideal is by definition going to contain the 0 element, so it's non-empty. So I can take an element. If I is x, the ideal generated by x1, then we are done. Why is that? If I is generated by a single element, it is of course finitely generated. So remember, our goal is to show I is finitely generated. Our goal is to show that I is finitely generated. You take an element, if it just happens that I is generated by that, we are done because it's finitely generated by that single element. If not, let x2 be an element of I minus x1. Remember, x1 is an I, so the ideal generated by x1 is certainly going to be contained in I. If they are equal, we are done. If not, I is strictly bigger than the ideal generated by x1. So we take an element that's in I, not in x1. So that means x2 is in I, but x2 is not in x1. Okay. Now we continue the induction step here. If I is x1, x2, we are done. Otherwise, see, if I is x1, x2, we are done because I is generated by two elements. So I is finitely generated, which is our goal. Otherwise, choose x3 inside I minus x1, x2. Right? And in the second stage, the ideal generated by x1, x2 is contained in I. Because x1, x2 are elements of I, so the ideal generated by x1, x2 is contained in I. If it is equal to I, we are done, we stop the process. If not, I is strictly bigger than the ideal generated by x1, x2. So we can choose an element in I that's not in x1 minus x2. And we keep doing this. So I'm going to define I1 to be the ideal generated by x1. I'm going to define I2 to be the ideal generated by x1, x2. So remember, I1 is contained in, we have, of course I1 is contained in I2 because I1 is just generated by x1, I2 is generated by x1, x2. So every element in I1 which is a multiple of x1 is already in I2. And now you can see that we can keep doing this. So let's say we have constructed I1, I2 up to IR or IN. How do we construct IN? It is generated by x1 through xn. And suppose if IN is equal to I, we are done. Because again it's finitely generated by n elements. If not, choose xn plus 1 inside I minus IN. IN is certainly contained in, remember each of these is contained in I. Every ideal that we are constructing is a sub-ideal of I. If it is equal to I, we are done. If not, we can choose an element which is in I but not in IN plus 1 and define. Now having chosen IN xn plus 1, we define and we set IN plus 1 to be x1 through xn comma xn plus 1. So we can continue this process. So and we construct an ascending chain of ideals in this way. So what we have is I1 contained in I2, contained in I3, contained in IN, contained in IN plus 1 and so on. And if you now use the assumption by hypothesis, this chain stabilizes, right? That's the hypothesis. So IN equal to IN plus 1 equal to IN plus 2 for some n. So there is some stage in this chain that you stop getting new ideals, you keep getting the same ideal every time. But that means, remember each ideal that we are considering in this case is a finitely generated ideal. So I must equal IN, which is, why not? Why must it equal? I'll just say this in words. I must equal IN because if it is not equal to IN, there is some element of I that's not in IN and we use that to define IN plus 1. So IN plus 1 would be in fact strictly bigger than IN and it will not be equal to IN, which contradicts this assumption. Okay, so that completes the proof. So I must equal IN at some finite stage. So that means I is finitely generated. So a ring is Noetherian if and only if every ascending chain of ideals stabilizes. Okay, this is useful. So I'll now give two applications of this. Two statements about one example and one statement about Noetherian rings using this alternate characterization of Noetherianness. So one example I want to give is the following. So let's define R to be the ring of continuous functions. So let me write it. Continuous functions from the real numbers to real numbers. And if you remember from one of the earliest videos in the course, we gave this as an example of rings, because you can add two continuous functions. Because the target is R, we can add f plus g to be f plus g of x to be fx plus gx. Similarly, we can multiply two continuous functions and it turns out to be a ring. We claim that R is not Noetherian. R is not Noetherian. So this is another example of something that's not Noetherian. We in the last video looked at the polynomial ring in infinitely many variables. That's one example. This is another example. So why is this true? So to prove non-Noetherianness, we either have to produce an infinitely generated ideal. More precisely, we have to produce an ideal which is not finitely generated, or we have to produce an ascending chain of ideals that does not stabilize. So we are going to do that. So we are going to construct an ascending chain that's not going to stabilize. Let's define In to be all continuous functions from R to R such that fx is 0 for all x at least n. Okay, so these are continuous functions which vanish beyond the point n. So it's an easy exercise to check that. In, so I am defining this for every positive integer. Check that In is an ideal for all n. That's because if you add two functions which have this property, that means they are identically 0 to the right of n. Their sum also has that property. If you take a function which is identically 0 to the right of n and multiply by any function, it will continue to be 0 to the right of n. So it's easy to check that it is an ideal, and also easy to check that you have an ascending chain like this, right? Because I1 consists of functions which are 0 to the right of 1, I2 consists of functions which are 0 to the right of 2. So if something is 0 to the right of 1, it is also 0 to the right of 2. So certainly we have this chain. So we have an ascending chain. So we want to show that it does not stabilize. But this chain does not stabilize. If it does not stabilize, R cannot be Noetherian, because if R is Noetherian, every ascending chain of ideals must stabilize. So why does it not stabilize? I claim that each stage we get a strictly bigger ideal. So define a function. So I am going to first draw a picture. So define f1 as follows, fn. So we can simply take any function you want up to n. This is the graph of that f. So I am drawing the graph first because it's easy to see. So up to n, anything that's non-zero, and to the right of n, it is 0. For example, this is just one example. So we can define x to be, fx to be, fnx to be, let's say x minus n, where x is less than or equal to n, 0 when x is greater than or equal to n. That's this function, right? So this function, then fn is of course continuous, and it is in In because it is 0 to the right of n, but fn, remember, is not in In minus 1. Because if you take n minus 1, it is not 0 on that x-axis, right? It is not 0 between n minus 1 and n. Okay, so that means that there is a function which is in but not in In minus 1. So In minus 1 is not equal to In for all n. We can define this function for every integer at least 1. So In minus 1 is not equal to In minus 1 is strictly contained in In. So you have a non-stabilizing ascending chain of ideals. Hence, by the previous exercise, previous proposition, R is not Noetherian. So in some sense, this example as well as the previous example are not Noetherian because they are too big in some sense. They are very big. There are ideals that are very big in the first case, and there is an ascending chain of ideals which does not stabilize. But interestingly enough, there is the following, maybe I should not write it as a remark. I should not write it as an example, but remark. A subring of a Noetherian ring can be non-Noetherian. What I am saying is that in general, subring of a Noetherian ring need not be Noetherian. As example would be, remember the polynomial ring in infinitely many variables that we looked at. That we looked at in the previous video, and that is not Noetherian because it has an ideal which is not finitely generated. But if you look at the this is certainly a integral domain. Polynomial ring over R is an integral domain. So we can look at the field of fractions of R. This of course is a Noetherian ring because it's a field. Any field is Noetherian because it has only two ideals. So both are finitely generated. So if any field is Noetherian, however, this ring which is a subring of this is not Noetherian. So non-Noetherian rings are strange. So you can have a Noetherian ring containing a non-Noetherian ring. So that can happen as this example shows. However, we do have a nice result, nice proposition we can say. Let R be Noetherian and let I be an ideal of R. Then the quotient ring is Noetherian. So I am not going to give the full proof. It's a good exercise for you to do. It just uses, so let phi be the natural map from R to R mod I. What is the natural map? Remember, it sends an element R to R plus I, the coset corresponding to R. So this is a natural ring homomorphism. It's a non-two ring homomorphism. Use the correspondence theorem. That's all I will say. Use the correspondence theorem to show that every ascending chain of ideals in R mod I stabilizes. Remember, a ring is Noetherian if and only if every ascending chain of ideals stabilizes in that ring. So to show that R mod I is Noetherian, it is enough to show that every ascending chain of ideals in R mod I stabilizes. So now how do we use the correspondence theorem to show that? Take a chain in R mod I, take the inverse image basically. Just take the inverse images of each ideal in that chain. Now that gives a chain of ideals in R. So this is because the correspondence theorem says that the bijection between ideals of R mod I and ideals of R that contain I is an inclusion preserving bijection. So if you have J1 containing J2 containing Jn, which is a chain in R mod I, phi inverse J1 will be contained in phi inverse J2, which will be contained in phi inverse J3 and so on. Now that's an ascending chain in R, but R is Noetherian, so it stabilizes. That means phi inverse Jn is equal to phi inverse Jn plus 1. But that means now again using the correspondence theorem, the ideals Jn must equal the ideal Jn plus 1, because if they were different, the phi inverses would also be different. Okay, so this is a hint for you, but finish the proof as an exercise. It's a good exercise to make use of several facts that we have so far learned in this course. The correspondence theorem, the equivalent definition of Noetherian rings and so on. So this proposition is nice because it gives us a way to construct new Noetherian rings if you have a Noetherian ring. If R is a Noetherian ring, we can construct a new Noetherian ring by just taking a quotient. That still leaves the question of how to construct Noetherian rings to begin with. What do we know? So far we know Z is Noetherian, any field is Noetherian, polynomial ring over a field is Noetherian. But the most important way for us to construct new Noetherian rings is what is called Hilbert basis theorem, which I will prove in the next video. So let me just end this video by stating this as a preview of what will come next. So this says that if R is Noetherian, then the polynomial ring in one variable in over R is also Noetherian. So this in particular will prove that Zx is Noetherian, though you could do that directly just using the definition. But now, and also it covers the case of a field adjoined X. K is a field, then K, polynomial ring over K in one variable is Noetherian. That's old example, that is not new. But Hilbert basis theorem does give new examples. This will now in particular tell me that we can say Zx1 xn or Rx1 xn are Noetherian. We can't put infinitely many variables, of course, then it will not be Noetherian, as we know. But finitely many variables, it's Noetherian. And for this, we need Hilbert basis theorem. And how do we get this? This is simply because polynomial ring in n variables is simply a polynomial ring in one variable over the polynomial ring in n minus one variable. So I'm going to do this in more detail later, so don't worry about it. But once you can adjoin one variable to preserve Noetherianness, you can keep doing this, and any finitely many variables you will preserve Noetherianness. So let me stop the video here. We have in this video looked at various examples of Noetherian rings. We looked at an alternate characterization of Noetherian rings using ascending chains of ideals, and we showed that if a ring is Noetherian, any quotient ring R mod I is also Noetherian. In the next video, we are going to prove the Hilbert basis theorem. Thank you.